Good day and welcome back to the enclosure. I thought I'd give you a quick update on what has happened since the last update after we had passed our electrical inspection. One of the things that I've completed is the commitment that I made to the building science community regarding putting in some full-time laboratories that are going to be built into the exterior wall structure of the house and be long-term testing over 12 to 18 months. And so I have finally completed or generally completed the 6 test panels. And so here's an example of one here. And what we're looking at is the inside face of the panel. So there's going to be drywall here, and then there's going to be a 10.5-inch dense pack cellulose cavity. And what we're measuring is we've got temperature down at the bottom and moisture content of the wood, which I'll talk about in a sec. Here we've got moisture content from the bottom up is temperature. And then the shiny metal thing, that is a humidity monitor. And then at the top, we've got, again, temperature is a little thermistor here, and the moisture content. So the moisture content, and I'll give you a close-up here, is basically 2 brass pins that are driven so that they are just below the surface of the outboard side of this sheathing. And then you just solder on some leads, and the software that will connect to this will measure the resistance between those 2 pins, and based on that resistance can tell how wet the wood is, which is basically how a moisture meter works. When you jab the pins of a moisture meter into a chunk of wood, that's basically what's happening. So we've got 6 different designs. This particular one was a double stud cavity, so it's simulating as if you had 2 sets of studs apart with insulation in the studs and insulation between the studs, and then sheathing on the outside and drywall on the inside. And you can see here we've got the drywall, got the insulation, and the sheathing. So I'm not simulating the thermal bridging of the structure. I'm only simulating what's called the center bay effect. So in other words, the nominal values of the insulation and the siding and all of that kind of stuff, so that we can get an idea on what walls perform better as far as heat flow through the assembly, as far as airflow through the assembly. So there's different air barrier strategies here. And most importantly, vapor and moisture flow through the assembly. So we're going to see that in some cases, some of these high performance wall systems, and the double stud specifically, may not be a wise choice for the Pacific Northwest, because the outside sheathing isn't exteriorly insulated. Therefore, it is always at the temperature of the outdoors. And if moisture-laden air leaks from the inside and heats that sheathing, it will condense. And so this system relies on a 100% complete and continuous air barrier. And in construction, that's very hard to do. In most cases, you're going to have holes somewhere. Even in the very low air change records of like passive houses, you still have holes in that dwelling somewhere. And where there is a hole, if it had that style of wall assembly, there will most likely be condensation. So we're going to measure it for a year's period. And then at the end of the year, we're actually going to introduce moisture at the exterior of the sheathing to simulate a leak in the siding or flashing during a rain event. and we're going to see how well the system can handle some water ingress, how forgivable the system is. So that's a double stud. Here it's a more standard system. It's very similar to what I have on the house, except it has a poly vapor barrier. I'm going to have which is considered a class 1 because it's very vapor tight. I'm going to have a class 3, which is fairly vapor tight, but if the wall ever wetted up, it would allow moisture movement to the interior. It'll just be a class 3 vapor barrier paint. So this is very similar to what I've got, except it's using vapor barrier as poly as vapor barrier. And it'll use the delta vent, which is what I use, the exterior membrane, the sheathing membrane as the air barrier. And then we've got, this again is very similar to what I've got, but it has no vapor barrier whatsoever. So we're not going to put the vapor barrier primer. It's just going to be straight latex paint, and we're going to see how important a class 1, 2, or 3 vapor barrier is when they're not installed. Going over to the other side, the other 3, we've got, this is no interior vapor barrier, so there won't be poly, there won't be vapor barrier paint, but there will be an air barrier, and again, the outside is going to be dense packed cellulose, mineral wool on the inside, and we're just going to see, it's considered or called a Larson truss, because a lot of times there will be this wide eye joist or truss that's put to create the dense cavity on the outside of the structural stud bay. And we're going to see how that performs. Panel 5 is a possible passive house wall. So it's got drywall, it's got rock wool fiber, it then has OSB that is sealed as air and vapor barrier, dense packed cellulose, and then it's got a wood fiberboard exterior sheathing, which we're going to test. This one's called Agipan or Agepan, depending on what you want to call it. And then finally, we've got this one. It is going to have exterior non-permeable XPS insulation. And so there won't be the ability to easily dry out to the exterior, and we're going to see how well that performs. So that took a little bit of effort. There was quite a bit of work involved in putting these on, and some of them I redid because I wasn't happy with how the cables were rerouted, so I redid them so that the cables are outside of the test area and run up the exterior of the panel. And those panels are going to be installed into the stairwell going down to the basement. So this area here is basically just a temporary insert. All of those studs will come out. I have a structural header, so there's no structural requirements of any of this. And the panels are going to slide in beside each other in this area and be sealed so that there's no interaction between the panels. There's no air movement, no vapor movement in the seams of the panels. And then we'll test it over time. And so that we have a baseline, I'm also comparing to our baseline wall, which is going to be, as I said, vapor barrier paint for our vapor barrier, then 3.5 inches of mineral wool from rock wool, and then 1/2 inch exterior sheathing, the delta vent exterior membrane, which is also detailed as the air barrier. So that's the primary water shedding surface or water resistant barrier, as well as the air barrier, and you can just see it wrapping around here on the lab. And then we have 6 inches of exterior insulation, a 3/4 inch rain screen, and then the cladding. And I've designed this so that you won't see any of the details from the outside. So it's just continuous siding, but if I press on that right now, because there's no panels there, it's fairly soft because it's got some movement without the structure. And the only thing that you will see if you look really, really, really hard is right there. You can see just the tip of a thermistor sticking out. And that is the exterior cladding temperature of our baseline panel. So I'll have several of those along the wall for each of the 6 panels that I'm to add. So that's the lab. I'm grateful that I finally got to it. I know that Rock will have been very, very patient waiting for this to get going, and I'm appreciative of their patience. And I also know that the scientific community is looking forward to seeing the results. The other thing that I've been doing is all of the ultra low voltage. So Cablevision, telephone, I'm not doing telephone, I'm just doing internet and intranet. And so I've got a whole bunch of Cat5 and coax runs, and I'll show you in the basement where they all terminate. Throughout the house, I have a lot. I think I've figured out so far I have about 3,200 feet of Cat cable and about 1,000 feet of coax. So there is a lot. There seems to be 2 schools of thought. One is go all wireless, and the other is put the cables in. They're relatively cheap and easy to do, and you're always going to have consistently better performance from cables if they're done right over wireless. And so, for instance, I've got 2 jacks, 2 LAN and 2 coax for the office, and then 2 facing this way for the hutch in the dining room. Who knows, we might put a digital picture frame. I've also, for instance, on the digital picture frame idea, this is going to be the art wall at the front entrance. There will be overhead lighting shining down, and I've allowed for a single bay, a single area, a Cat5, so that we can have a digital picture frame. And I can put up some of the photos that I've taken over the years from Sucre Harbor House or Tofino or Sunshine Coast or that kind of thing that I like. The other thing that we've done is, or I've done, is put in the rough-in security system. So that basically involves running, I guess the only one here would be down there. It's basically an 18.2, and the reason it's at the bottom is because these doors have the ability to become venting. And what I mean by that is, I'll try to see if I can show this in profile. The top of the door swings out. And so I wanted the ability, it hinges from the bottom, as you can see here. I wanted the ability to have, especially upstairs, windows and doors open during the evening or during the night, and still have the exterior of the house secure, have the alarm on. And so the only way to do that is to place the sensor at the bottom non-hinged side of the opening window or door. So here's another example. The sensor is going to be mounted right here, and that'll catch when the window opens normally, or it won't catch when the window is in vent stage, because the bottom is still going to be tight enough that it's going to close the magnetic reed switch. So that's been completed. All of the operable windows and doors have been wired. The keypads have been wired. They're 4-conductor. Can't remember if it was 18 or 16 gauge 4-conductor for the keypads. What else? Yes, let's go down to the basement and we'll see the results of all of the ultra low voltage wiring. It's been fairly intense. It was, and I still have to secure all of the cables. I'm doing that last so that I'm only doing it once. And so here you can see everything coming in, and it's a fairly large bundle. And if we go into what I call the cold room, which is the room under the garage, which is going to have the node 0 location, which is where all the low voltage comes to, you can see what we've got. So we've got the yellow and the blue is all of the cat cables, and this represents the upper floors. I still have the basement to do, which I'm going to do at a later point. And then we've got all of the alarm system, which is what's here. And then we've got all of the coax coming in. And so I'm going to have a node 0 wall-mounted station here where everything terminates. And that'll be where the internet provider's modem goes, whether it's high-speed fiber optic or Shaw, I'm not sure yet, but it'll come to this location. There will be a conduit that goes from this location out to the telephone pole where the services are brought to. And then the last thing I did, you can just see a coil of it here, is I ran the conductor along all of the vacuum pipe for all of the vacuum head or ports power, which basically it just tells the system to turn on. It's not high voltage, it's just a signal wire, and it tells the system to turn on. I chose not to go with powered ports. I have enough plugs throughout the house near where the ports are that'll be easy just to get this style of wand, which has a separate electrical cable to run the power heads. But you can see here, I haven't spliced them up. I'm only doing the parts of the house that are going to be completed before occupancy. So I've been just putting in the basics and leaving the rest. But upstairs, I've completed the splicing. I've also completed all of the basement anchoring of the interior non-bearing walls, so the partition walls. I chose to use Hilti anchors. You can also use concrete screws. You can use pneumatic or Hilti driven, like the explosive driven nails into it. I find that the nails often split the concrete and spall it out, and this just provides an extra level of securing in the case of an earthquake. These aren't structural, but because they are bolted to the floor, they will provide a lot of lateral stability if there is ever an earthquake, and improve that. I've also put in the partition wall for the shop. So this wall here, from that point to this point, will remove. It unbolts, and it'll allow for large items to be brought in and out of the shop. So you can see it's bolted to the floor, and it's bolted to this side, and there will be access panels and it's also bolted to the top. And there will be access panels that will allow me to know where those bolts are, and I'll just unbolt the wall whenever I have a large item that I need to get in or out. Another thing that I did was I capped off any open ports on the shop air system, so I could pressurize it and test it before I insulate the upper floors, but now I have shop air inside the house, and this has been extremely convenient. So the black hose is coming from the compressor that's out in the shop at the back of the property, and it's pressurizing the system, and then I've been using the pneumatic hammers and staplers on the main floor where I have a port For instance, to do the lab. All the lab panels were stapled together. As you can see by this inserted photo, I also tested the first of the two toilets that we've purchased for our hanging toilets, or our in-wall toilets. So this is going to be the one that we're going to use for the guest bathroom on the first floor. And couldn't really put our thumb on it until we came across this one. And no pun intended. It's a very unique design, and it certainly will be a conversation piece. I've also wired up a port that will be beside the bathroom sink, and that's going to connect to an RCA jack that is going to go behind the shower, and the shower has auxiliary input ports for sound, so that instead of listening to the radio, you can listen to anything that you can stream through a 4.5 millimeter port. So any of your music that you've got on your phone, on your laptop, your tablet, whatever. And I'll just quickly show you what the shower looks like. It's upside down, and you may or may not be able to see it with a bad light. So that's it. We're still generally keeping the house heated with these two heaters. I've moved the small fan onto the main floor. I think it's currently on medium. Yeah, it's currently on medium. And the oil heater is currently on high, and we're currently at 18.3. I did set up a 30 amp heater in the basement now that comes on periodically. On the nights, if we have several nights in a row that are 10 degrees or more like 5 degrees or less, and we haven't had any sun during the day to warm the place up, it starts to get down, and I've had it as low as 16. But as soon as I turn that 30 amp heater on and turn these both to high, I'm back up to 18 within a couple of hours. So the performance of the house has been outstanding. So what I'm basically doing now is I'm just going through all of the things that need to be figured out before the insulation of the walls and the first floor ceiling, and everything that needs to be completed in order to pass my framing inspection. So one of those things is figuring out the ceiling hydronic heating and cooling panels. And I've recorded a little video that I'll show right now. One of my next tasks is to order the materials that I need for the radiant ceilings throughout the house. And I think I've shown you this graphic in the past, but this is a design from John Siegenthaler's book. And it is 3/4 inch of insulation in between hydronic heating transfer plates. They're aluminum transfer plates. And then the PEX tubing, which is typically an aluminum PEX or a PEX that has some form of oxygen barrier, is snapped into the groove. Now, there's a lot of different manufacturers of this type of material, so I got some samples, and this one's from Roth, and it comes in large sheets. I think they're 4x6 or 4x8, and it would have made my life a lot easier because the assembly is all in one. So like you can put up a lot of material in a very short period of time without a lot of effort. But I have done quite a bit of research in the past on transfer plates and had ended up at a website from Radiant Design and Supply. And their website is www.radiantdesignandsupply.com. And on it, there is some videos showing the heat transfer via different types of transfer plates. And so what they do is they have a side-by-side, same flow, same temperature of fluid, and they do an infrared showing how that energy from the tube is transferred to the plate and out, or not, as the case may be. And one of the issues is how well the omega shape fits the tube. So this one from Roth, this is the tube that they gave me. This is standard PEX A Uponor tube, and this really says it all. They're really that's just because it's bent a little bit, but there's really no clamping force there. It just slides right through, and it's not just that panel. They basically all do the same thing. And the problem is that it doesn't really conform to the shape of the tube. There's a lot of space between the pipe itself. You can see it's moving around quite a bit. And so unless you have intimate contact between the aluminum and the PEX tube, you're not going to get very good transfer rates. You're going to almost rely on the tube to provide a radiant transfer to the plate instead of a conductive transfer to the plate. In comparison, the plates that Radiant Design and Supply do, they're a much thicker aluminum than the standard plates, but they have optimized the shape of the omega, where when you snap this in, it's in. And there's no space around here whatsoever. It's tight. You can pull it, but not easily. It's in there, and it's going to have really good transfer rates between the tube and the plate, which is obviously what you want. You don't want the energy just to flow through the tube and out of the room. You want it to transfer to the aluminum transfer plate, where it can then radiate down into the room. So I had hoped to avoid the problem with the stuff from Radiant Design and Supply is this is all you get. You get a plate that's, I believe they have 8-foot long plates, or they might even have 12-foot long plates. And you have to then build the system that goes in between each plate. And I'm going to have it at 6-inch centers, and so I'm going to have to be cutting foam at that required thickness, glue it up temporarily until I can get the drywall on and screw everything in place. So I had hoped to avoid that extra work, but with the difference in fitment between these two, it's kind of a no-brainer. And on the Radiant Design and Supply site, they show some of the other competitors' plates profiles as well. They have close-ups showing that there's a really large gap between the two. So the path is clear. I'm going to have to go with the Thermal Fin U 1/2 inch from Radiant Design and Supply, and kind of do the extra work to mount it. But it'll be worth it in the long run as far as efficiency of the system. Okay. So as you can see, the evidence was pretty clear on which way I need to go. So I'm going to start figuring out the quantity required of the plates and get them ordered and coming up. I'm also working on getting a York exterior heat pump for the system. I'm still working with Therm Atlantic on the inside guts of the system, the DX2W, which will be what actually creates the hot water. And otherwise, I'm going through item by item and figuring out what we need to get ordered and getting that process started, so that hopefully sometime in December we could start insulation. And that will be great if we can get to, say, January and maybe start putting in drywall. Okay, thanks for visiting, and we'll talk to you again soon.